Hello everyone, welcome to my YouTube channel. Today I'm solving Leetcode question burst balloons. You are given n balloons, indexed from 0 to n-1. Each balloon is painted with a number on it, represented by array nums. You are asked to burst all the balloons. If you burst the ith balloon, you will get nums I-1 times nums I times num I plus 1 coins. If I-1 or I plus 1 goes out of the boundary of the array, then treat it as if there is a balloon with a 1 painted on it. Return the maximum coins you can collect by bursting the balloon wisely. For the given example, nums equals 3158, the output is 167. So the maximum, the optimal strategy to collect the maximum coins is to first burst the balloon 1, and then by burst balloon 1, you can collect coins 3 times 1 times 5. And then your nums will become 358 because this one has already been bursted. In that case, you burst the balloon 5. You will collect the coins 3 times 5 times 8. And then the remaining nums is 3 and 8. So now you need to burst a balloon. You burst 3. Remember, it says if I-1 or I plus 1 goes out of boundaries of the array, then treat it as if there is a balloon with a 1 painted on it. So that's why we add 1 to the left boundary. So that's how we collect 1 times 3 times 8 coins. And then there is only 8 remains in this num. So in that case, you burst this balloon, so you collect 1 times 8 times 1. So that's the number of coins you collect. So in the example 2, so in this example, the optimal strategy is to first burst the balloon 1. In that case, you can collect 1 times 1 times 5. That's 5 coins. And then you have a 5 left in the nums. In that case, so remember, whenever we go out of the boundary of the index, we pad 1. So in that case, when you burst 5, you collect 1 times 5 times 1. That's also 5 coins. So in total, you collect 10 coins. So this one is pretty, from the example, you can understand, okay, how this burst balloons work, but it's not very intuitive to figure out an algorithm to solve this one. So let's think about how to break down this one into some subproblem. So let's try that. So basically the idea is, let's say, okay, if we can break this problem into subproblem to solve. So one strategy, so idea 1. So the first idea is, okay, so basically, let's say if you burst a balloon K, so let's say if you burst a balloon index K, so after that, can you break down to the subproblems? Let's say to consider, okay, what is the maximum coins in the nums? Let's say from I to k minus 1, and the maximum coins from nums k plus 1. So this one, the first idea is, let's say if you first burst a balloon with index k in nums, and then after you burst that balloons, this balloon is no longer available. So in that case, can you break down to 2 subproblems? Let's say to consider maximum number of coins from index 0 to index k minus 1. Remember, like when we're trying to slice the array, so this does not include k. So this is from index 0 to index k minus 1. And this is from index k plus 1 to the end of this nums. So basically, the first idea is, let's try to first burst the balloon index k. And then after that, can we break down to 2 subproblems? Let's say from index 0 to k minus 1. and then from k plus 1 to the end of array? The answer is no. So why the answer is no? So here, I mean, after you burst the balloons with index k, and then you consider, okay, these two, they are actually not independent of each other. What do I mean by not independent of each other? That means, let's say, after you burst the balloon index k, so basically k minus 1, k plus 1, k plus 2, minus 1. So, okay, so this is the array like this. After you first burst the balloons with index k, so you remove this one. Now the balloon with index k minus 1 and k plus 1, they become adjacent to each other. So when you burst the balloons, you need to consider those two as well. So since they are adjacent to each other, so you cannot break them down to two independent subproblems. So the first idea is not working. So the idea 2 is, let's try to tweak it a little bit. So basically, it's similar to the first idea, but here, instead of first burst balloon index k, we last burst balloon index k in nums. And then after that, we can break down to two subproblems. Nums, why we can do it this way? So let's say think about this one. So we last burst the balloon with index k in the nums. So this is the original array, input array. So we have the k in that. So we assume that, okay, since we last burst this balloon, so before we burst this k, all these balloons to the left of k, so from the index 0 to the index k minus 1, has already been bursted. And then all the balloons from k plus 1 to the end of the array have also already been bursted, because we assume that we last burst this balloon in index k. Okay, so in that case, if we burst the balloon index k, we can break down them into two subproblems. So that's kind of a little bit trick we are doing here, is trying to break this problem into subproblems to solve. So if you last burst of the balloon with index k, so okay, last burst balloon with index k. In that case, balloons, that means, okay, last burst balloons with index k, that means balloons index 0 to k minus 1, and then balloons with index k plus 1 to m minus 1 have already been bursted, burst before balloon with index k is burst. So that's kind of the meaning. And then we break down into two subproblems. So in that case, the maximum coins. So when we burst the balloons as index k, we get the nums, let's say k minus 1 times nums k times nums k plus 1 coins. So that's kind of based on the problem statement. If we burst the balloon k first, we get this number of coins. So what if right now we burst balloon k with index k last? So in that case, it's the nums. So basically, that is number from the I. So from that's, let's say that's the 1 times nums k times 1. Remember, we add 1 to the left boundary and then also to the right boundary as well. So that is what if we burst in the entire nums. So out of the entire nums, we burst this one, the balloons with index k last. However, so right now, so let's think about the range, let's say, for between index I and j. So that means, okay, burst balloons between index I and j, not including I and j. So basically, we're trying to think, okay, let's think about burst the balloons between the two index I and j, and then I and j are not included, which means you are bursting the balloons between index I and j, but you are not bursting balloons at index I and j. So in that case, so what is the coins? So what's the number of coins to collect? So let's say first balloon index, first balloon index k, lastly between balloons of index I and j. So basically this idea is, let's say, okay, let's take a look at all the balloons between index I and j, and then we choose an index k out of those balloons, and then we assume that we burst that balloons lastly. So in that case, what is the number of coins to collect? So in that case, it's just simply numbers I times nums k times nums j plus, so that's kind of, so remember, so here the balloons of index I and j, they are not bursted, so it's like, okay, they kind of like serves as the boundary, so they are not bursted yet. We are just burst the balloons between the index I and j, not including index I and j, and then we choose an index k. Let's say, okay, this is the last balloon to burst between all the between the balloons of index I and j. So in that case, by bursting these balloons, we collect the coins. Number of coins is nums I times nums k times nums j. So in that case, we break down this one to a subproblem. So in that case, let's try to first code up the solution. So the first solution we are going to code up is going to be a recursive approach. Basically break down the entire problem into the subproblems to solve. And then for the recursive approach, so we are using a top-down approach, basically recursive with memoization, to avoid the repeat calculation. So in that case, let's say, let's keep a cache. And then let's break down to the subproblem. So define a helper function, I and j. So basically this helper function is number of coins to collect by bursting balloons between index I and j. Remember, note that balloons at index I and j are not bursted. So in that case, what is the stopping condition? So stopping condition. If I is greater than j, so in that case, we just return 0. So that's our base case, the stopping condition. And then if not, so if I, j not in cache, so in that case, we need to calculate the I and the j. So in that case, so basically for k in range I plus 1, j, for all the possible index between the index I and the j, we just check. So basically, the number of coins we can collect by bursting this one, by bursting these balloons, and then maximum of this plus, let's say, helper I to k plus helper k to j. So, okay, so what does this mean? So basically, every time, so we are trying to, let's say, we assume that the uh, balloon with index k is the last, to, is the, we burst this balloon with index k last between the balloons of index I and j. So when we burst these balloons, we collect this number of coins. So that's the nums I times nums k times nums j. So, and then before that, all the balloons between the index I and the k are bursted. And then all the balloons between the index k and j also burst. Remember, so this helper function for ij, not including the ij. So all the balloons between index I and j are bursted, but the balloons at index I and j are not bursted. And then so that's kind of okay. So this part is the total number of coins we collect if we burst the balloon at index k last. And then we just keep comparing it with the existing answer to see if it's the maximum. And then after that, we got the cache I, j equals the answer. And then in the end, we just return from the cache ij. So that's kind of our recursive function. So before calling this recursive function, so one thing is we want to check everything before the index and the I and the j. So, and remember, if in the original problem statement, let's say if I minus 1 or I plus 1 goes out of the boundaries of the array. In this case, which means I and j are out of boundary of the array. So this should be padded with a 1. So to make the problem simpler, so we just modify the nums. So the nums equals 1 plus nums plus 1. So we pad the 1 to both ends. And then in the end, so we can just call helper on the index I and the length nums minus 1. That is between the number we pad. So remember, right now after we pad 1 to both ends of the original nums array. So the number at the index 0 is the padded one. The number at the index less nums minus 1 is also the padded one. So basically, we want to get the number of coins we can collect by burst all the balloons between this index 0 and the index of the last nums minus 1, and not including the balloons at index 0 and index last nums minus 1. So which means we are not burst the balloons we padded to the both end of the original nums. So let's run the code. Okay, so we passed the provided test case 3158 and output the correct output, but we run into time limit exceeded error. So now we are going to actually optimize this solution to improve the runtime. I'm pretty sure this logic is correct. So now it's just like, let's think about ways to optimize this one. So in the coding interview, the interviewer would usually expect you to come up with the recursive solution. And then after that, we can discuss the methodology or the solution, the optimizer solution. So to optimize that, so one way to optimize the this kind of problem is like we usually start with the recursive approach. We go from the naive recursive approach to the recursive approach with memoization. That is the top-down approach. So here we already implement the memoization. The next one is optimization is dynamic programming approach with the bottom-up approach. So in that case, let's try to code it in the dynamic programming approach. I would recommend to start with the recursive approach because it's very intuitive to come up with a recursive approach by break down the original problem into the subproblems, and then from there you can go you can continue to the dynamic programming approach. So for the dynamic programming approach, I'm just going to use the create a DP array. So basic DPI j, it means the number of coins to collect by bursting balloons between index I and j. Not bursting balloons at index I and index j. So this is very similar to our helper function. So dpij means the number of coins to collect by bursting balloons between index I and j. And we are now bursting balloons at index I and index j. So which means we just burst the balloons between the index I and j. So in that case, it should be, let's initialize with 0, so 0 coins. So before creating this dp, so let's try pad the original nums array. So we pad that, and then n equals the length of nums. So in that case, we can do it this way. So times n, and then for this in range n. So what we are going to return, so eventually, so our result should be dp 0 and then n minus 1. So that's kind of very similar to the how you return this helper function in the recursive approach. So now we construct our table, dynamic programming table. So here we are trying to calculate the values. So for I in range n minus 2, minus 1, minus 1. So let's do it n minus 3. For j in range I plus 2, I plus 2, and then, so we are trying to calculate dpi j. So that's for k in range I plus 1 j. Our dpi j equals the maximum of dpi j and the nums I times nums k times nums j plus dp I k plus dp k j. So basically this part corresponding to our original recursive approach. So in the recursive approach, we also calculate its maximum. So this part we just cover. It's very similar to how we do it in the recursive approach. And in the end, we just return dp 0 and minus 1. So let me try run the code first and submit it. Okay, now we get a working solution. So let me go back and then examine this dynamic programming approach one more time. So most of the part is very intuitive. Let's say you can find there are like a lot of very similar to our solution, how we implement the recursive approach. It just instead of using a cache and top-down approach, we use bottom-up approach and we create a DP table. So here we first pad the ones to both ends of the original nums, so, and then we get the length of this new or padded array, and then we create a DP table. So it's a two-dimensional matrix, and then dpij, it means the number of coins to collect by bursting balloons between index I and j. So between the index I and j, not including index I and j. So we are not bursting balloons at index I or index j. So it just means, okay, after we burst all the balloons between index I and j, how many coins we can, the maximum number of coins we can collect. So in that case, our result should be the dp0 and dp0 and n minus 1. Remember, right now after pad the ones to both ends of the original nums, so this dp, the 0 refers to the padded one on the leftmost end, and n-1 refer to the padded one on the rightmost end. So we still burst all the balloons in the original input array. So here, the one of the most confusing part about this dynamic programming approach is, okay, how to loop the index I and j, because the remaining part is, let's say, for k between range I plus 1 and j is we burst the balloons at index k last when we are bursting balloons between index and ij. So we just try for each position. Okay, what if, for example, what if we burst the balloons at I plus 1 last? What if we burst the balloons at I plus 2 last? What if we burst the balloons at j minus 1 the last? So in that, for all those options, so what's the number of coins we can collect? And then we just compare and then select the maximum one to assign to DPI and J. So this one is very intuitive. So in that case, so remember, when we are burst the balloon at index K, the last, here the only coins remains are the boundary coins at index I and j, and then the coins at index k were burst. So in that case, this is the number of coins we collect. And then before we burst the coin at index k last, we burst the coins at index between index I and k, and then also the coins between index k and j. So that's why we add dpik and dpkj. So this part is most straightforward. So okay, the most challenging part for this dynamic programming approach is how to determine the index for ij in the loop. So here I'm starting from I'm doing it backwards. So for j, I mean, it's kind of easier to understand. Let's say for j, because we are trying to consider the balloons between index I and j, so we want to at least have one balloons between I and j to burst. So that's why for the index of j, that start from I plus 1. Because remember, we are bursting the balloons between index I and j. So we want to have at least one balloon between I and j. So, okay, that one balloon, the index of that balloon is I plus 1. So in that case, that's why our j start from the range I plus 2. So this is kind of straightforward. Okay, so then why we loop the index I starting from minus 3 and then all the way to index 0. So think about this case. So let's say the reason why we do it in a reverse order here for I is before you are calculating the dpij, you are calculating the dpik and then dpkj. So here, this dpkj, the k is greater than I. So because that's index k is index between I and j. So in that case, before we calculate the dpij, we should have dpkj already calculated, and this k should be greater than I. So that's why we're doing this loop iterate over I in the reverse order, starting from n-3. So this is my solution for burst balloons. If you like my video, please feel free to subscribe to my YouTube channel. Thank you.